Today I am introducing a new topic, critical thickness of insulation. When you hear about thermal insulation, the first thing that comes to your mind is insulation always reduces the heat transfer, which is a misconception. In case of plane surfaces where addition of a layer will always reduce the heat transfer irrespective of the quality of the insulation material. But for small diameter wires and spheres, addition of insulation sometimes will have adverse effect by increasing the heat flow. This is mainly due to decrease in convection resistance due to a larger exposed area. The thickness of the insulation for which the heat transfer is maximum is known as critical thickness of insulation. Now we will see how the addition of insulation on a cylinder affects the heat transfer. Now let us consider a small diameter wire which is a solid wire, and another one is a hollow. R1 is the outer radius. This is a solid wire which is a small diameter wire, and this is a hollow one, and again outer radius is R1. The surface temperature is T1 and ambient temperature is TA. So here also surface temperature is T1, ambient is TA. The length of the wire is L. Here length of the hollow cylinder is L. Now we will see how the heat flows from the outer surface to the surrounding. From the surface to the surrounding, the heat transfer is by convection. So you have Newton's law of cooling, Q is equal to HA delta T. But here the heat transfer coefficient I represent by H0, that represents the outside heat transfer coefficient. So H0 into area, outside area, into temperature difference. Temperature difference is T1 minus TA. So that will give the heat transfer from this solid wire from the outer surface, that is for a bare wire. So this is a bare wire. From the outer surface, the heat flow is given by H0 A into T1 minus TA. The same is here. Temperature difference is T1 minus TA, and area is same radius is there. So area is also same radius, same length. Area is also same. H0 is a heat transfer coefficient. So the heat flow from this surface to the surrounding is same, H0 A into T1 minus TA. Since we are only considering the heat flow from the outer surface. So we are only considering when the temperature of the outer surface is T1, how the heat flows from the outer surface to the surrounding. So you can rearrange this equation, T1 minus TA divided by bringing H0 A to the denominator, you will get 1 by AH0. So that is the heat transfer from the bare wire. The heat transfer is given by T1 minus TA divided by 1 by AH0. Now consider the same wire, solid wire, and this hollow cylinder insulated with an insulation material with thermal conductivity K. So its outer radius of the insulation is R. So the same solid cylinder is insulated, outer surface is insulated, and the radius is R, and the thermal conductivity of the insulation is K. Now this hollow cylinder is also insulated with outer radius R. Now we can get the heat loss from this insulated wire. We are considering the heat flow from the surface of this cylinder, solid cylinder, and again from the outer surface of the hollow cylinder. So heat flow from here to the surrounding. So in the heat flow part you have two resistance. One is conduction resistance through this insulation and convection resistance from the outer surface to the surrounding. So by adding insulation you have this increased resistance due to conduction. Earlier we had only convection resistance. So here I add only convection resistance, and convection resistance was 1 by AH0. But in this case we have conduction resistance, which is given by 1 by 2 pi KL log R by R1, where R is the outer radius and R1 is the inside radius. So this is conduction resistance due to this insulation, and you have convection resistance 1 by AH0. But here the area is not same. In case of a bare wire, when it was not insulated from the outer surface, the convection is happening, and the same equation was there, convection resistance 1 by AH0. But the area of this cylinder, outer surface area, was less in that case, because after insulation, the diameter has increased, the outer radius has increased, the convection area has increased. So this quantity, the convection resistance, has decreased. Now the convection resistance is decreased due to the larger exposed area, whereas this is the addition of resistance. So compared to the previous equation, this is resistance in this case. In case of bare wire, or bare cylinder, hollow cylinder, the convection resistance is 1 by H naught. But in case of a insulated wire, one term has added, but there is a decrease in convection resistance. Conduction resistance is added, there is a decrease in convection resistance because of the increased convection area. The area of the outer surface has increased, so the convection resistance has decreased. Now this is the heat transfer from the insulated wire. Now we need to compare the heat loss from the bare wire and insulated wire. So for insulated wire, the heat transfer, when it will be maximum? When the denominator is minimum. When the denominator is minimum, you will have maximum heat transfer. This quantity, if it is minimum, you will have QA maximum. So R is a variable. We are finding out the R, radius. At what radius you will have minimum value of this resistance, total resistance. So to find out that, you can take the denominator and differentiate that denominator and equate to 0 and find out the radius at which this quantity will be minimum. So therefore, for maximum heat transfer, we will take the denominator. For minimum quantity of denominator, you differentiate that denominator and equate to 0. So I have written the denominator here, and the differentiation, the variable is R. So differentiated with respect to R. So I have expanded this log R by R1, you can write it as log R minus log R1. So once you write this as log R minus log R1, 1 by 2 pi KL you can multiply 1 by 2 pi KL into log R minus 1 by 2 pi KL into log R1 plus 1 by IH naught. A I will replace by the outer area. The outer area is 2 pi RL. For a cylinder, outside peripheral area is 2 pi R circumference into L. That will give the outside exposed area. Okay. Now you have to differentiate with respect to R. So differentiation of log R is 1 by R. So 1 by 2 pi KL into 1 by R. And this quantity R1 is a radius of the bare cylinder or hollow, outer radius of a hollow cylinder. So R1 is a constant. K, L, all these quantities are constant. So this term is a constant. So differentiation of that will give 0. Now when you differentiate this quantity, 1 by R differentiation is minus 1 by R square. So 2 pi L H naught will be there, 2 pi L H naught. 1 by R differentiation is minus 1 by R square. So you get minus 1 by 2 pi R square L H naught. That is equal to 0. So here 2 pi L R, 1 R here. 2 pi L R will cancel. You have only 1 by K here. 2 pi L R goes, you will get 1 by K, and 2 pi L R, so you get only R H naught. So 1 by R H naught. So 1 by K minus 1 by R H naught is equal to 0. 1 by K is equal to 1 by R H naught. So you get R is equal to K by H naught. So this radius, you are getting a solution for the outer radius for which the heat transfer is maximum. This particular radius is known as critical radius of insulation. So critical radius of insulation is K by H naught. For this radius, if you are insulating the wire or a hollow cylinder with this radius, then the heat transfer will be maximum. So RC is equal to K by H naught is known as critical radius of insulation. So critical radius depends on thermal conductivity and heat transfer coefficient. If thermal conductivity is high and heat transfer coefficient is less, the critical radius will be more. So poor quality of insulation and low heat transfer coefficient will increase the critical radius. Poor quality of insulation means higher thermal conductivity, and low heat transfer coefficient also decrease the denominator, and that will increase the critical radius. If a critical radius for a wire or a hollow cylinder is more than the outer radius, then addition of insulation with this particular material will always increase the heat transfer. Now you can calculate the critical thickness of insulation as critical radius minus outer radius of the wire. So critical thickness of insulation is RC minus R1, and we know the critical radius is K by H naught minus R1. This will give the critical thickness of insulation. Thanks for watching. Keep watching this channel for more such videos.